Hey everybody. So today we're going to be talking about absolute dating. So last time when we spoke, which was last week, we focused in on something called relative dating. And if you remember from relative dating is the idea that we can tell what age rocks are or different layers beneath the Earth's surface, how old they are based off of um, whether or not they are close to the surface or below the surface, or if something intruded or came through the layers, we could determine the ages that way. Well, that's inexact because, as we learned last week, right, layers could fold over, and there's exemptions or differences or things that can happen that can alter our understanding of relative dating. And so, what we're going to be talking about today, and this isn't too long of a video, is something called absolute dating. And absolute dating is just like the word means absolute. It is pretty much right on point. There's not a lot of wiggle room for how old it is. But this method is going to use something called radioactive decay. Okay. And we're going to use that in terms of being able to date the absolute age of a rock, fossil, or event. All right, so absolute dating. Again, I read the definition before. It is using radioactive decay to determine the exact age of a rock, fossil, or event. Now, what do I mean by radioactive decay? For all intent purposes, radioactive decay just means that um, as we age, or as our fossils are left behind, right, or as a rock is left behind, um, the atoms that are left behind, they become isotopes. Okay, and isotopes are when you end up losing um, a neutron from your inner core. Okay, and over time this breaks down, and it's over a set period of time. So sometimes something radioactive decays um, every 10 years, or something will radioactively decay every 10 minutes, depending upon the amount of time every specific substance will decay at a specific rate. Okay, so how do scientists do this? All right, to figure out the radioactive decay. The first thing they do is they drill for core samples. So you can see here in this particular picture here, there's this long tube right here that was at one point into the ground. They drilled directly into the ground, and then that brings the layer back up to the surface. Step two in the process is that now they're going to crush those samples, and they're going to crush them into very thin sections. So they'll take the sample and they'll crush it up, and it'll make it into a very, very fine powder. Okay, and if you looked at that fine powder under the microscope, you would see something that looks like this. They kind of stain it out a little bit too, and you can get different colors. Just showing you the different minerals and substances that could have been in those layers. And the third step, is that they're then going to analyze them. Now, this is where they put things either through a type of machine, or they look at it under a microscope and they search for what is it made of and what are some things that probably shouldn't be in that layer. Now, that sounds a lot like when we did relative dating, except this time, instead of saying we think this isn't supposed to be there, we know it's not supposed to be there, because when we chemically look at the chemical composition of that particular layer, we realize that, why is this here? This makes no sense. And we can eliminate that and pull it out. All right, the fourth step. Now, you have geochronologist. The word chronologist just means time, and then someone who studies time. And geo has to do with like the earth, right? Geology. They're going to use something called a spectroscope to measure the ratio of stable to unstable products. So this is what this looks like. This is a crazy machine right here. Okay, a spectroscope. A spectroscope just is going to look at what are the wavelengths that are being emitted off of that substance. They're actually pretty neat. They're very, very complicated. You can get them actually much smaller. I used smaller ones when I was in college. Okay, so those are the steps that geologists will do. Now, this right here is our periodic table. Now, at what you see here are all the different elements. If you've taken chemistry before, you've used this a lot. For those of you who have not taken chemistry, you're probably going to do chemistry next year, and you're going to be using the periodic table a lot. And every element on here on the periodic table will decay at a particular rate or break down at a particular rate. Okay, so isotopes, again, I'm just going to go back to this word here, this idea of they have the same atomic number. So, and you look here, the atomic number is 5 or for boron, or 6 for carbon, or 7 for nitrogen, 8 for oxygen. Isotopes are going to have the same atomic number, but their mass is going to be different. So for example, if something has stable carbon, all right, carbon has 12 mass units, okay? We call that carbon 12. Okay. An isotopic carbon has a mass of 14, and that causes it to be carbon 14. So this is a different version of carbon 14 that exists, okay, within nature. But that one is a little bit more unstable. That one breaks down over time. So this is the most important thing about absolute dating. If you take nothing else from this lesson, okay, the biggest thing you should take from this is something called a half-life. Half-life is the time it takes for the unstable product to decay into a stable product. So just how you just saw that carbon 14 is going to take a period of time to decay and break down into carbon 12. So what half-lives mean is that in that given sample, half of the atoms are going to decay to a stable product, and the other half that's left behind is going to stay radioactive. Now, this comes back to that whole idea I told you that everything breaks down over a set period of time. So what you end up getting is you end up getting something that has elements ranging in half-lives from maybe a fraction of a second to billions of years. So what happens is that half of the unstable isotopes that are left will break down into stable. And then what's left behind will have to go through another half-life. And then you'll go through another half-life and another. So this is in your reference table on the first page. You have your radioactive isotopes, the ones that we care about for Earth Science class. And we have carbon 14, potassium 40, uranium 238, and rubidium 87. And this just is telling you, remember, the unstable product is carbon 14. And what it's going to break down into is nitrogen 14. So you don't necessarily break back down into carbon. You disintegrate into something else. So carbon 14 is going to disintegrate into nitrogen 14. And the half-life that it takes is 5.7 times 10 to the third years, or in other words, 5,700 years that takes. All right, so these are your half-lives. If we were in school, we would have done a really cool lab where you take a bunch of pennies and then you go through the half-lives and you graph it out, and it would have been a lot of fun to have done it that way. I'm going to try and find some kind of activity for you to be able to do this week doing that as well. So with absolute dating and the half-lives, nothing affects a half-life. Half-lives are going to happen regardless of any environmental factors. So temperature doesn't speed it up or slow it down. Pressure doesn't speed it up or slow it down. Any type of chemical reaction is not going to slow it down. Every unstable isotope is eventually going to go through a half-life and lose half of it all the time, regardless of the environmental factors. Okay, so if we talk about uranium-238, uranium-238 is one of the most important isotopes when we date rocks. It has a mass of 238 units. When it decays, it breaks down from uranium-238 into lead-206. Its half-life is around 4.5 billion years. So why is this so important? Well, let's go back to the formation of the Earth, right? The Earth was formed how many years ago? Around 6.5 billion years. So that means that a piece of uranium-238 that could have been around the beginning stages of the Earth being formed has gone through one half-life already. And it's going to go through another half-life, whatever's left, in another 4.5 billion years. Carbon-14 is really important when we talk about dating organic remains. This is a much smaller range because it's only within tens of thousands of years. So carbon-14 has a mass of 14. When it disintegrates or decays, it breaks down from carbon-14 into nitrogen-14. And why do we care about this with organic remains? Well, if we go back to the uranium half-life, that was 4.5 billion years. 4.5 billion years isn't going to work for organic remains because those creatures aren't going to live for 4.5 billion years. We need something that has a much shorter half-life because that allows us to be able to go not as deep into the geologic history. So the half-life of carbon-14 is around 5,700 years. Now this helps a lot when we talk about dating organic remains because we can get really, really accurate in terms of when that particular fossil or other type of organic remain was left behind. Okay, so I'm going to set back up for 1 second here. So that's the story for absolute dating. We're going to do a small activity this week on this. I have a fun activity planned for Wednesday, so if you're here for Wednesday, you're going to have a pretty, really, really, really great activity. All right. Other than that, make sure you keep getting your work done, turn stuff in, make sure you get it done, all right? All right, I'll talk to you all later. Take it easy, stay safe, stay healthy. Talk to you all later. Bye-bye.